Hi, and welcome back to another extreme value theory video. In this video, what we're going to consider is how we can implement a GLM-style extreme value model using our code. To do this, we're going to return to the Amazon share price data that we considered last week and see if we can improve the model fit by allowing the parameters mu and sigma to change depending which quarter of the year we're in. To do this, we're going to use our code that's available on the course Moodle page. And if I can share my screen with you, you should hopefully be able to see the folder that you can download for yourself. The folder is called Week 3 Amazon Seasonality, and it contains several files. The one that we're interested in here is main.r, with the other files just being involved in the processing of the data that I've scraped from the internet in order to get it into this workable format. So if we go ahead and open up main.r in a new RStudio session, and if I scroll up to the top of the file here, then what we can see is that we're looking at the Amazon data that we were looking at before, so the monthly maximum negative returns, and we're going to consider fitting two models to this. An IID model, so the same model that we considered last time, and a seasonal effects model, where we're going to let each of the location parameter mu and the scale parameter sigma depend on which season we're in. And we're going to do this in a discrete manner. So we can have a separate location parameter in spring, summer, autumn, and winter. In order to fit these models, we're going to need the ISMEV package again. So we can load that by running line 5, and we can read in the Amazon data by running line 6. Using head to take a look at this data, then we can remind ourselves of its form. It's a data frame with 3 columns. The first one gives the year of the observation, the second one gives the month of the observation, and the third column gives the maximum negative return within that month. What we're going to need to fit the second model is a fourth column in this data frame called quarter, and that's going to take the value equal to the quarter of the year that we're in. So it'll take the value 1 if we're in spring, 2 in summer, 3 in autumn, and 4 in winter. Running lines 10 through 15, we can see that we've added this column. So to get some motivation for why we're actually wanting to fit this model in the first place, the next section of code creates a plot of these monthly maximum negative returns. And making the plot much larger, what we can see, if I remake this now, is the maximum negative returns colored by which quarter of the year they're in. And just giving this a quick eyeball, it seems as though some of the largest losses are happening in the blue and green months, so in the last half of the year. What we want to do is try fitting some models to see if we can improve the model fit by letting the extreme value parameters vary depending which month we're in. So this plot is what motivated this sort of model construction. If I squish that back down again now, we can start and look at how we might fit the model. And to begin with, we're just going to recreate the same model that we had last week using gev.fit and providing that the argument xstat, which is simply our monthly maximum data. So we're saving this in an object called Amazon_IID, which, as you'll recall, is a list of 10 items where some of these describe, for example, the MLE values, the standard errors of those estimates, and their covariance matrix. In order to fit the model where the parameters change within each quarter, what we're going to need is a design matrix. and this is going to be made up of 4 columns. The first column is going to be entirely made up of 1s. It's going to represent our intercept term for each parameter. The second column is going to be an indicator variable for being in quarter 2. The third column an indicator for being in quarter 3, and the fourth column an indicator for being in quarter 4. So if we run lines 40 through 44, we can construct that design matrix and check that it has the form that we expect. So the first column is entirely 1s, represents our intercept. Column 2 is an indicator of which observations were made in quarter 2 of the year. Column 3, an indicator for the third quarter, and column 4, an indicator for the fourth quarter. It's important that we don't include an extra column here with an indicator of being in the first quarter, because what that would mean was that the sum of the indicator variables was equal to our intercept column. That means our design matrix would be rank deficient and wouldn't be invertible, and that's going to lead to problems when we're trying to estimate our coefficients. Another potential downfall when constructing this design matrix would be to make it so that you only had 2 columns, an intercept column and a second column that simply gives the value of the quarter that you're in. What fitting this type of model would do would be to treat the quarter variable as a continuous random variable rather than a discrete. What that would mean is that you're trying to fit a linear trend in quarter, and rather than having a separate model parameter for each quarter. So if we want to use this design matrix to fit a GEV model where the parameters are functions of these indicator variables, then we can again use the gev.fit command to do this. And we're going to store this saturated model in an object called Amazon Seasonal Saturated. The first argument of this gev.fit command is going to be the same as before, our vector of monthly maxima. The second argument, ydat, is then our design matrix that we've just constructed. And then we're also going to want to specify through the inputs mu L and sig L, which columns of that design matrix we want our parameters to be dependent on. So here, we're going to specify that we want mu to depend on the second, third, and fourth columns of the design matrix. We haven't included a 1 at the front here, because like with a linear regression model, R automatically includes an intercept term. So if we had included this 1, we'd lead to problems with matrix inversion when we're trying to fit this model. Because we're trying to fit a saturated model, we're letting the location and the shape parameter be distinct in each of the 4 seasons. So we have 6 inputs here. We can also specify how we want the parameters to vary as a function of the covariates through the specification of what link function we want to use. So for the shape parameter, just going quickly back to the shape parameter, if we want to keep that constant, then we specify that as being null rather than specifying it as only having an indicator. And when we're specifying the link function that we're using for each of these parameters, so there's an equivalent mu link and shape link function here. What we're specifying is not the link function as we've introduced it, but the inverse link function. So here we want to use a log link, so we specify the exponential function as the link for sigma. If you don't specify anything in here, it will use the identity function. So if we run lines 50 through 56, we get our fitted seasonal saturated model appearing. And we also get a warning message, and that's saying that the square root of the diagonal of the covariance matrix has led to NAs. All that means is that when we're trying to estimate the Hessian around the MLE, we ended up with a non-positive semi-definite matrix. And so you end up with some negative variances being produced by the numerical methods. If we were interested in this model, then that would be a problem. But fortunately, we don't get that far. If we start off using forward selection, so trying to add in one parameter at a time to each of the scale and location parameters, we keep whichever of those gives us the most significant improvement, if any give a significant improvement. And it turns out that only adding an indicator for Q3 to the location parameter mu gives us a reasonable improvement. So if we look, for example, at adding a Q2 indicator term, so allowing the location parameter to be different in the second quarter of the year, while using only an intercept term for the sigma and psi parameters. Here we've specified using an identity link for the location parameter and a log link for the scale parameter. So if we look at fitting this, we can then extract from the fitted IID model and the fitted seasonal model the negative log likelihoods and use those to calculate the deviance. We can then use this deviance to perform a likelihood ratio test and calculate an associated p-value. So you can see that the probability of a deviance, at least as extreme as this, under the null model is quite high. We've got a p-value of 0.42. So adding in this separate location parameter for the second quarter doesn't provide a significant improvement. So we've got lots of models to run through and try and test here, but the most significant one that comes out is adding in a Q3 indicator for the location parameter, which gives us a p-value of 0.06. So we'd be fairly surprised to see this sort of improvement if the null model were correct. If we're working at the 5% level, this wouldn't be sufficient evidence to suggest there was an effect, but I'm going to choose here to work at the 10% level, just so I can show you some more examples of how to use code with this. So we're going to go ahead and use this model where we have a distinct location parameter in our GEV model for the third quarter, and all of the other parameters are constant. So in much the same way as we did last week, we can extract the MLE component of this fitted model using the $ syntax. And here all I'm doing is storing that in a separate object called seasonal MLE, and in line 82 adding names to those to make it a bit easier to interpret the output. So if we run lines 81 to 83, we see that the location parameter in months 1, 2, and 4 is given by this value, our point estimate of 0.028. And in the third month, this is going to be decreased by a small amount, where our point estimate is a decrease of size 0.0036. The constant parameter sigma is estimated to be the exponent of this value, so something very small. And the psi parameter is estimated to be 0.33. So we've got slightly heavy tails going on here. So what we can look at in line 85 is the estimated location parameter. Sorry, this shouldn't have an exponential because we're using the identity link function. The estimated location parameter for seasons 1, 3, and 4. And if I remove the exponential also from line 86, we see that the location parameter in season 3 drops from 0.028 in the other seasons to 0.024 in the third season. And as we saw before, we can get confidence intervals for each of these coefficient estimates based on asymptotic normality by simply adding on and subtracting the correct number of standard deviations. So here we see that the 95% confidence interval for the, sorry, this is not the 95, it's the 90% confidence interval for the month effect on the location parameter just does not cover 0. It's entirely below 0. And our estimated shape parameter psi is estimated to be anywhere between 0.22 and 0.44. So we conclude that we do have heavy tails in this case. One final thing to note is that you can continue to make diagnostic plots in the same way as before using the gev.diag function. And this takes your fitted model as an input. So if we create these plots, what we can see is that we only get a PP and a QQ plot constructed in this example, where before we had the return levels and the fitted distribution also plotted. It's important to note here as well that in the quantile plot, the model quantiles and the empirical quantiles have been transformed to account for the covariate values. So all of our observations have been transformed onto a common Gumbel scale here. The probability plot doesn't have this difficulty in interpretation, and so is unchanged from what we had before. Great, that's everything I had to run through in this session. Hopefully now you feel better prepared in how you can use R to fit these types of model. If you have any problems, feel free to get in touch, and if not, I look forward to seeing you on Friday. Thank you.